Okay, so this is the first part of section 11.2. It's dealing with a new chi-squared test. This one is called chi-squared test for homogeneity. In the first part, we're going to deal with the chi-squared test for homogeneity. In the second part of this section, we'll deal with a chi-squared test for independence. They're very similar in the calculations and how you perform the tests. It's how we get the data, whether we get it from one sample or multiple samples, is really the main difference. And the null hypothesis and alternative hypotheses will be stated a little bit differently from each other as well. In chapter 10, we compared two proportions from two different populations or two different samples, but in this section we're going to want to look at, well, what if they have more than just two treatments or two populations? What if we have three or more? So we're going to be looking at a two-way table, and two-way table is a good way because we'll be able to look at two different random variables at the same time. So like in the last section, we dealt with M&Ms. That was one random variable, the color, right? Categorical variable, which was the color of the M&Ms. Here we'll be looking at two different categorical variables, and so a two-way table will be helpful here. The first example that we look at in this section then is going to be looking at sort of an experiment where we apply three different treatments on three different nights in a restaurant, and the treatment is either no music is playing, French accordion music is playing, or Italian string music, say like a violin, is playing. And then under these conditions, they recorded how many French, how many Italian, and how many some other type of entree are ordered at this restaurant. So we collect data and notice that we have a different number of entrees totally sold each night. So it's hard to look at these numbers, just the numbers themselves. So like, for example, we see that when French music is playing, the French entrees sold quite a bit. But since these numbers, the total number of entrees sold every night is not consistent, we can't really look at the numbers. And so what we're going to want to do is look at the resulting proportions in each case. So right now, calculate, I'll show you the first one, and then try to calculate your proportions for the other one. So when no music is playing, what's the distribution of entrees ordered? So the French, we sold 30 out of 84. The Italian is 11 out of 84, and the other type of entrees is 43 out of 84. So do that for the other two situations. Okay, so we have the following distributions for the other night. So we have no music playing, French music playing, and Italian music playing. All right, so there's a lot of numbers to look at here. 9 different numbers, 9 different situations. It's hard to sort of look and see, well, what's going on? Well, ultimately, we want to really compare the different types. What was the change in the type of food ordered based on the type of music played? So it might be good to, in the way of a bar graph. Now we know these aren't histograms because they're categorical data. So create bar graphs for each one. So for no music playing, for French music playing, and for Italian music playing. Okay, so basically what this chi-squared test is endeavoring to do is to see, are these distributions the same? So is when no music playing, when French music playing, or is it when Italian music playing, does it affect these distributions, the percentages of each of the types of entree that is sold on those evenings? So here they're trying to get us to say a few sentences about these distributions. So the bar graphs in the last slide are helpful in trying to state a couple things. Pause this and write a couple things, and then play again, and we'll see kind of, I'll read through what I have on mine. All right, so the entrees that the customers tend to eat differ considerably depending on what music is playing on the particular evening. And then, just a couple things. We can say that the Italian is rather low when the French music is playing, and it's certainly higher when the Italian music is playing. It's about 26%, 23%. Or even when no music is playing, it's still pretty high. It's 13%. All right, French entree seems to be popular no matter what's playing, but certainly is more popular when French music is playing. And then the other entrees, the non-French, non-Italian entrees, tend to be a little bit consistent regardless of what music is playing. So it's about 50% to 41%, something like that. So it tends to not vary as much when based on the music. Okay, so we were looking back at when we looked at all 9 of those proportions and trying to compare them, it gets a little bit complicated. So what we're trying to do here is come up with a way of comparing all of those proportions sort of at the same time. So the overall test that we're going to use here, the chi-squared test for homogeneity, is going to test if there's good evidence of any difference among those parameters. All right. So again, we're looking at the p-hats from the statistical data, but we want to sort of say stuff about all nights when the different musics are playing. So we're talking about really the parameters. Ultimately, if we sort of decide that there is a difference between the distributions under the 3 different conditions of music, then we'll want to do a follow-up analysis, and we'll do an example of that in our example that we go through. Okay, so the chi-squared test for homogeneity, we're going to start our 4-step process with, of course, our null and alternative hypotheses. So the null hypothesis is going to have the key words, there's no difference, right? Unlike in the goodness of fit test, we said for the null hypothesis that the distribution is the same as it is claimed, and then we said it's not the same. So here we start with there's no difference in the distributions based on the categorical variable. So categorical variable here is the type of music played, and then the alternative is going to be that there is a difference. Okay, so that's going to be kind of a reverse. Before we said they're the same and they're not the same. Now we say there's no difference and there is a difference. All right, so to calculate, so here's the data that we got in the previous, that we saw in the previous table. What we want to look at is figure out what the expected counts are. So we are, the null hypothesis is saying that the distribution for all 3 nights, for the no music, French music, and Italian music, for all 3 nights, the distribution is really the same. So it's really going to be, looking at this data here. So in other words, when no music is sold, the amount of French food is the same as the proportion in the last column of 99 divided by 243. So what we want to do is calculate the expected value of French food when no music is playing. We're going to look at the following. We're going to take these numbers. We're going to take the row total, which is the 99, and multiply it by the column total, which is the 84, and then we're going to divide it by the table total. So, I mean, really it makes sense if you think about it. If this ratio of these 2 numbers is really the same under all 3 music conditions, then if we started with 84 entrees one night, then the ratio of these 2 times the 84 should tell us our expected value. So in order to find the expected value, we take the number we're looking at, so this 30, we take its row total, 99, multiplied by its column total, which is 84, and then we multiply it by, divide it by the table total, which is 243. All right, so but that has to be done for all 9 cells in this case, for every single cell. So it gets a little bit cumbersome. When they get to be rather large, we'll use computers to generate those for us, and we won't have to calculate all of those by hand. Okay, so some conditions we want to, again, randomize as usual. We want to, or randomize experiment, not sample more than 10% if we are sampling. Otherwise, it's if it's an experiment, then we don't have to worry about the 10% rule. And then the expected counts, again, these have to be the expected counts. These are the ones that we're calculating. They all have to be greater than 5. So that's for all of the cells in our table, our two-way table. All right, and then when we find all of those, and actually right now I'm going to ask you to calculate the 3 bottom values in the amount of other entrees sold under the 3 conditions of no music, French music, or Italian music. So pause this video and calculate those, and then resume. Okay, so here we are, the actual expected values. Okay, so now once we have our 9 observed values and our 9 expected values, we can calculate the chi-squared statistic value, and it looks a lot like we did for goodness of fit, except for the goodness of fit, it was in a one-way table. Here we've got a two-way table. So we have to calculate this for all 9 cells. We add them up for all the values for all 9 cells. So we have to do this 9 times, square them, do the difference, square them, divide by the expected, and then add all 9 of them up. All right, so calculate a couple of these. I don't know that you need to do all 9 of them, but at least calculate a couple of these. Okay, so we're going to again add up all 9 of the terms for all 9 of the cells, and we end up with a value of 18.28. Okay, so again, we want to look at how big that is. So, or is that statistically significant? And so we look again. We use the same process from here on out to get our p-value. All right, so let's look at the specific null hypothesis for this case. Pause the video and then write down what you think those are, and then we'll talk about them. Okay, so the null hypothesis is that there's no difference in the true distribution of entrees ordered at the restaurant when the 3 musical conditions are being observed. So no music, French music, or Italian music. The null hypothesis will be the exact same wording, except there is a difference. Remember too that these null and alternative hypotheses are based on not the statistics. So it's not looking at the actual observed values, but whether the observed values are evidence that the true parameters for all such nights when music is playing in different conditions, whether there would be a difference in the entrees. All right. So remember that even though we're kind of thinking about these values that we observed under the 3 music conditions, that the null and alternative hypothesis, we are talking about the parameters, all possible nights in this restaurant when these 3 musical conditions are applied. All right, so we calculated our chi-squared statistic of 18.28. Let's look at how we would calculate our p-value from our chi-squared statistic. So we do have tests in our calculators, except they're a little bit cumbersome to use because you have to really be able to work with matrices. If you feel comfortable working with matrices, you can certainly use it. But let's do it by hand and then use our chi-squared CDF command to actually get our p-value. Or we can also, well, first let me show you how to do it on the table. So we want to calculate our degrees of freedom, and here our degrees of freedom are the number of columns minus 1 times the number of rows minus 1. And so we have a 3 by 3 table, so our degrees of freedom will be 2 times 2, or 4. So now we go to the chi-squared distribution, and we look at row number 4. And now we look in row number 4 for our value of 18.28, and we see that it's between 16.42 and 18.47. Clearly, it's going to be much closer to the 18.47. But for now, we can say that our p-value is between 0.001 and 0.0025, of course, knowing that it's going to be a much closer to the 0.001 because 18.28 was much closer to the 18.47 in our interval there. If we do this in our calculator, it will give us a more precise value of 1.0011, and indeed we were right in that it was much closer to the one side lower end of that interval that our table was capable of giving us. All right, so how would we interpret this p-value in context? Pause this video and then I'll reveal it and we'll talk about it. Okay, so the p-value is interpreted a lot like we normally are, right? Assuming the null hypothesis is true, the p-value is the probability we would get a value as extreme or more extreme than the one we got. So here we'd say, assume that there is no difference in the true distribution of entrees ordered at the restaurant when no music, French music, and Italian music is played. So in other words, the null hypothesis is true. Then there is about 0.1% probability of getting a difference in the distribution of entrees like the one we saw, or larger, just by chance. All right, so what conclusion could we draw if this was going to be a 4-step process? Go ahead and write your conclusion, and then pause it while you're writing it, and then we'll review. Okay, so our conclusion is a lot like they have been in the past in any of the significance tests. So we do 3 components, right? So the p-value is less than our alpha. We reject the null hypothesis. We have convincing evidence that, and then the alternative, that the difference in the distribution of entrees ordered in the restaurant when no music, French music, or Italian music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that was played, because this was an experiment, right? So since we randomly assigned treatments, we can show causation in this case. All right, so for the chi-squared test for homogeneity, we've got on this slide, we've got a list of the sort of the generic form for the null and alternative hypothesis. Again, the null hypothesis is going to say something like there is no difference. The alternative is going to say there is a difference. The chi-squared statistic is calculated exactly the same as the goodness of fit, except we are going to have to calculate an observed minus expected quantity squared over expected for each of the cells in our two-way table. The degrees of freedom are calculated not by just the number of categories, subtract 1 from that. In this case, it's going to be the number of rows minus 1 times the number of columns minus 1, and then that will give us our degrees of freedom. If we're using the table, we look at the row and look for the chi-squared statistic in the row to get the equivalent p-value range. All right, so we want to do a follow-up. In this case, we did reject the null hypothesis, with the same example of no music, French music, and Italian music played at a restaurant. We did reject the null hypothesis, so we want to do a follow-up analysis. So before we even get to that, let's look. Below here is the Minitab printout for this particular situation, and you can see that there are 9 cells, and each cell has 4 values in it. Before we get to that, You notice at the top we have the three different conditions of music: no music, French music, Italian music. And then on the left side, they don't have the entrees listed as French, Italian, and other. They just list them here as 1, 2, and 3. But each cell has, as you can see, 3 numbers in it. It has the observed number, so that's the number of entrees ordered when Italian music was, the number of French entrees, I think, when Italian music was sold. How many you would have expected, assuming the null hypothesis is true, and then the contribution. Remember, all 9 of those contributions are what get added up to give us our chi-squared statistic. Okay, so we want to, since we rejected the null hypothesis, we want to now look at, okay, where were the differences the biggest? So we want to look at these 9 contributions and say, okay, well, where were they the largest? And so clearly here, these cells had the biggest difference between the observed and expected, and as a result, gave us the biggest contributions. And so now we just want to say that. We want to say in our follow-up analysis where the biggest contributions are, but also what direction they were. Were they the expected value, with observed values greater or less than the expected? And then in what situation. So looking at our output, we see that just 2 of the 9 contributions made up the chi-square statistic, contributed about 14 out of the 18 values. So just those 2 alone made up about 77% of the chi-squared statistic. All right, so we are led to a specific conclusion: orders of Italian entrees. That was the row number 2 in our Minitab printout there. That the orders of Italian entrees are strongly affected by Italian and French music. So the when French music was playing, we saw much fewer Italian entrees ordered than you would have expected. And when Italian music is playing, we saw much more Italian entrees ordered than you would have expected. Okay, so let's do an example of a chi-squared test for homogeneity. All right, has modern technology changed the distribution of birthdays? With more babies being delivered by planned C-section, Mrs. McDonald's statistics class hypothesized that the day of the week distribution for birth would be different for people born after 1993 compared to people born before 1980. So the idea is, of course, that there are more C-sections that are planned in the hospitals now, and so would the fact that you could decide what day to have the baby born, would it affect the distribution of the day of the week on which babies are born compared to before 1980 when maybe there were fewer planned C-sections? All right, so for example, why would they plan a C-section on the weekends when the staff on the hospital is smaller and there's not as many doctors working and that kind of thing? So to investigate, they select a random sample of people from both age categories, so earlier or later when they were born, recorded the day of the week on which they were born. The results are shown in the table here at the right. Is there convincing evidence that the distribution of birthdays has changed? So in other words, do these data support the fact that there is a difference in the distribution of birth dates for people born before 1980 and people born after 1993? Perform an appropriate test of significance. Okay, so they have a table. This is basically a Minitab printout. We have, remember, the first data in each cell is the observed count. The next one is the expected count. The following third value is the contribution, all of which will be added up to get our chi-squared statistic. The first thing we want to do is fill in the missing values. Normally, the Minitab printout would have all of those. I purposely erased some of them so that you could do some of the calculations your own. So the first 2 cells for Sunday born before 1980 and Sunday born after 1993, you need to calculate the expected value and the contribution. Pause the video, calculate those, and then we'll proceed. Okay, so we have the expected and contributions for those two cells. Now let's work on our four-step process. They're asking us to perform an appropriate test of significance. Essentially, are the distributions the same for before and after planned C-sections were prevalent? So here's the state. Come up with your null hypotheses. Here, the null hypothesis is that there is no difference in the true distribution of birthdays for people born before 1980 and people born after 1993. The alternative hypothesis is just that there is a difference. And then, of course, we'll state our alpha level as well. Okay, so plan. The inference procedure we're going to use here is the chi-squared test for goodness of fit. Sorry, not for goodness of fit, for homogeneity. And then check your three conditions as well. All right, so chi-square test for homogeneity. We sampled from two independent random samples, people born before 1980 and people born after 1993. We can assume that there are more than 770 people born before 1993 and more than 730 people born after 1993. And then if we look at all the red values, all the expected count values from Minitab, all the red ones are more than 5. So we're good. And so now do, calculate your chi-squared, and then calculate your p-value. If you're not using your calculator, you'll use your chi-squared distribution table. In this case, we don't really have to calculate your chi-squared statistic. All we really have to do is add up all of the third numbers in each of the cells. It's not a bad idea to show the part of the calculations. You notice I didn't show all 9, but I showed the first couple and the last. That way, if I did something wrong, I would still get some partial credit for knowing how to calculate it, even though I goofed and I did something wrong. The degrees of freedom, there are 2 columns, so 2 minus 1 is 1, and there are 7 rows, so 7 minus 1 is 6. So 1 times 6, the degrees of freedom are 6. Looking at your chi-squared table, your chi-squared statistic on row 6 of 6.549 is less than 7.84, so that means our p-value is greater than 25%. So that's as good as we can do if we are looking at our chi-squared table to calculate our p-value. If instead we use our calculators and use a chi-squared CDF, we put a lower value of our statistic, the upper value of 1,000, degrees of freedom of 6, and it gives us a more accurate value of about 36%. All right, so now write your conclusion. All right, so the conclusion is the same format as what we saw before. We are comparing our p-value to our alpha, so our p-value is greater than our alpha. Therefore, we fail to reject a null hypothesis. There is not convincing evidence that there is a difference in the distribution of birthdays for people born before 1980 and those born after 1993. So since we came up with since we did not reject the null hypothesis, we typically do not then go and try to do a follow-up analysis. That's only done when we reject the null hypothesis, so we will not perform a follow-up analysis here. Remember, when we're looking for the follow-up analysis, we're looking for where the big differences are. Well, we're kind of saying there is not a difference, so so we would not bother with that follow-up. Okay, so part B here is asking us to interpret the p-value in context. Remember, generally it's saying the p-value is the probability we would get a difference as big as we got or more extreme just by chance alone, assuming the null hypothesis is true. But of course, we want to say that in context. So write that out and then pause the video while you're doing that, and then we'll reveal it. Okay, so assuming the distribution of birthdays before 1980 and after 1993 are not different, in other words, the null hypothesis is true, there's about a 36% chance or 36% probability of observing the difference in the distributions among the two age groups as large or larger than the one we found in this study. Okay, so we have some homework on this section. Be on the lookout for 4-step problems.